let's start our move into three-dimensional quantum mechanics. Now, I think we're going to find that a lot of stuff, especially early on, is very similar to what we've done before, very similar to physics. But of course, when we're adding more dimensions, we're going to be adding more mathematical complexity. And so here we have a vector R with its x, y, and z components. And so now we have our same time-dependent Schrodinger equation. And our capital psi now is going to be, instead of being a function of just one spatial dimension, now we assume this can be a function of three spatial dimensions. And so we got a few things we're going to go through and just sort of adjust in our time-dependent Schrodinger equation. So first of all, the probability of finding a particle in the 3D region of some differential element dx, dy, dz is just what we would expect. The absolute square of the wave function times that volume element. And our normalization condition is going to be the same thing over all space. That's going to be equal to 1. So again, when it comes time to do this sort of thing, it's the same ideas we've been using, just a little bit more, I think, mathematical complexity. And furthermore, we've dealt with the operator that represents momentum, and we've been dealing with these. And so now we can separate three of these, one for each spatial dimension. And so we've been using py or px, but we can also write out py as so, and pz. This gets a little bit cumbersome, so we like to combine these into one piece. And so we're going to say that the total vector momentum operator that represents momentum is I h bar times the del operator, which you've probably seen this before, but it doesn't hurt to go through and discuss this a little bit more in depth. And so this is the operator here of these three partial derivatives in their vector directions. So again, this is a vector in the x direction, a vector in the y direction, and a vector in the z direction. And so over here we can write our Hamiltonian in three dimensions, same sort of way. So it's p squared over 2m plus our potential, although now our potential or our momentum is this vector here. And so if I write this out, we'll get 1 over 2m. And if we square this up, we get the momentum in the x direction squared plus momentum in the y direction squared plus momentum in the z direction squared plus z. And if we work through this, we get 1 over 2m. And when we square these guys, we get negative h bar squared d dx squared, negative h bar d dy squared, negative h bar d dz squared, plus our potential. And so, writing this all out, we get negative h bar squared over 2m del squared plus z. And so this del squared is the Laplacian, and this just works out to be these three partial derivatives added up like such. And so that's how we can write our time-dependent Schrodinger equation in three dimensions. So, the time-dependent Schrodinger equation, and just like last time, all right, we can say that if our potential is independent of time, the TDSE, this is the time-dependent Schrodinger equation, is separable, just like in Chapter 2. And so we can find solutions to capital psi in terms of our lowercase psi as a function of r, and then actually the same time-dependent piece we had before. So again, this is the new piece that's dependent on 3 spatial dimensions, and we left with our same time-independent Schrodinger equation. So this will boil down, again, very similar case to last time, just now that we have this mathematical complexity of 3 dimensions. And so the time-independent Schrodinger equation is going to be key for us. So here it is. And we're going to find, just like before, that we're going to be able to write any solution as a sum, a linear combination with Cn coefficients of these separable solutions. Now, we're going to find that many of the applications we make in 3D are going to be with what we call central potentials. And a central potential is a potential, so our potential is assumed to be a function of r, but ends up being only a function of the absolute value of r. Like so. And so potentials that only depend on the distance from the origin. And for example, we're going to look at the hydrogen atom, and so we have a really heavy proton that we'll just assume is at the origin, and then we'll use our vector r coming from the origin. And so if we imagine that our potential here is our electron, and so that potential, the Coulomb potential between them, only depends on that distance from the origin. And so that's going to make spherical coordinates super convenient. So the next step for us is to go through and remember a little bit, refresh our memory a little bit about spherical coordinates.